In this video, we're just going to review some of the concepts we've talked about so far dealing with multivariable calculus. So first of all, finding the distance between 2 points in 3 dimensions. This really isn't any different than doing it in 2 dimensions, right? We take the square root and we do the difference between the x's. So from -2 to 7, or from -2 to 5 is 7 units, and you could certainly use a formula, but I'm just going to do this. From 4 to -1, this is 5 units apart. And the z's from 6 to 3 is 3 units apart, so you could calculate that. Which of the points is closest to the YZ plane? Well, let's quickly draw the axes here. Remember, this is Z, this is X, and this is Y. So if I'm saying what point is closest to the YZ plane, I'm talking about this plane back here, it's the point that has the X closest to 0. So this point, this coordinate, is only 2 units away from the YZ plane, but this one is 5 units away. So closest is -2, 4, and 6. All right, find the point if it's projected onto the XZ plane. So we're taking this point and we're projecting it onto here, which means that it has a Y coordinate of 0 because it's just on the XZ plane. The rest remains the same, so it becomes -2, 0, and 6. All right, moving on. The equation of a sphere with a radius. Well, I'm going to write this just right below. Remember, we do x minus the x coordinate plus y minus the y coordinate plus z minus the z coordinate equals 16, the radius squared. Now, it says find the equation of a sphere with that center. Okay, well, we start off the very same way. We do x minus the x coordinate, so of course it becomes plus y minus the y coordinate plus z minus the z coordinate equals, and now if I know what the center is and I know a point on the sphere, I have to do distance formula between those two to see how far apart they are, and that will give me the radius. So let's just quick do that. The radius is equal to square root. So the x's from -2 to 5, the x's are 6 units apart. The y is from 2 to 7, they are 5 units apart. And the z coordinates from 5 to 2, they are 3 units apart. So we've got 6 squared, which is 36, plus 5 squared is 61, plus 9 is 70. So the radius is the square root of 70, but of course in our formula over here we do the radius squared, so it will just be 70. Find the components of the vector that has a tail of that coordinate and a head of that coordinate. Well, remember that we do this, tail and head. So we got to figure out how did it move from x, or from the first to the second. So here you'll see it went back 3 units in the x direction. Here from 7 to 4 it went back 3 units in the y direction, and from 1 to 3 it went 2 units up in the z direction. So our components in that first bullet are -3, -3, and 2. Okay, they reflect our movement. Back 3 in x, back 3 in y, and up 2 in z. Now it says find the unit vector for that. Well, we need the magnitude of this vector, so I'm just going to write the magnitude will be the square root 3 squared, or -3 squared, -3 squared, and 2 squared. So 3 squared is 9, plus 9 is 18, plus 4, it is the square root of 22. So my unit vector will be the same direction, but have a scalar of 1 over the magnitude. So it will look like that. Okay. Find the dot product between two vectors. So you remember we do the x's multiplied together, so 12. The y's multiplied together, so 2. And the z's multiplied together, so 6. And we just add those up. 12 plus 2 plus 6 is 20. So that is our dot product. And to find the angle between those vectors, if you recall, we do that the angle is equal to the inverse cosine of the dot product divided by the magnitudes. Okay, so let's just add these up in our head. 3 squared is 9, plus 1 squared, so 9 plus 1 is 10, plus 3 more, or 3 squared more, so square root of 19. Here, 4 squared plus 2 squared plus 2 squared. So 16 plus 4 is 24. So you would type this into your calculator, and that would give you the angle. And finally, a review of our scalar and vector projections. Remember, notationally, this says the scalar of B onto A, and this is the projection of B onto A. This gives me the scalar, or the length of that projection. This gives me the actual vector, or the components of that projection. And just a reminder visually what that projection is. It's like saying if B were dropped down at a 90-degree angle onto A. Okay, my angle might be a little bit off. And I like to think about this like it's this green vector then. Okay, so the first thing we do is we find the length of that green vector. We do that with this first formula. So let's figure out what the components are. For B, it went over 2 and up 4. Okay. For A, it went over 4 and up 1. So if I dot those two, A dot B, I've got 8 and 4. So 8 plus 4, the dot product is 12. And if I find the magnitude of A, 4 squared plus 1 squared is 17. So it is the square root of 17. This is the length of that green vector. Now to find the components, you recall we basically take our scalar that we've just found and multiply it by the unit vector of A. And that all simplifies down to this formula. That's why it ends up with this squared in the bottom, is because essentially it was A over magnitude A and A dot B over magnitude A, so the magnitude is squared. So really, all I have to do is do my dot product, square my denominator, so square root of 17 squared is obviously just 17, and multiply it by vector A. Okay, so 12 over 17 multiplied by 4, I'm going to just write this down here. This would be 48 over 17 and 12 over 17, like that. So these are the components of this green vector. 48 over 17, just over 3. 12 over 17, just under 1. So you can see those are the components of that green vector.